exponentials really act a lot very similar in their style. So maybe make a note of that. Logarithms are the inverse of exponentials. Okay. So the first thing that we're going to do is we're going to play on that information that logarithms and exponentials are related to one another as inverses, and we're going to be writing an exponential as a logarithm. And then also writing a logarithm as an exponential. Being able to move back and forth from the two different styles, okay? So if it's an exponential to start off with, it would look something like this. You would have some sort of base with an exponent, and it's equal to something else. That's an exponential equation out of that. That can be rewritten into a logarithm by rewriting it as log base a of y equals x. Okay. So the base of the exponential becomes the base of the logarithm. Okay, so that base of the exponential, base of the logarithm. It's a base in both areas. Okay. Logarithms are always equal to exponents. So whatever the exponent is on the exponential, that's what the logarithm is equal to. Whatever the exponential is equal to, that's what you're taking the logarithm of. Okay? So it's just manipulating the position of things. That's going to help us later on in the lesson solve some equations because we can turn them into things that we've done before. And that's one of the things with math is we try to make it look like something we've already done. So changing it from logarithm or from exponential to logarithm. To go from logarithm to exponential, so if you had log base b of x equals n, just changing up my letters so that we got to think a little bit. To change that to an exponential, the base of the logarithm is going to be the base of my exponential. So the base of the logarithm, this is read log base b. So log base b, so b is my base. The logarithm is always equal to the exponent. So the exponent is what the logarithm is equal to. So it's n. So it's b to the n power equals x. So converting from exponential to logarithm, from logarithm to exponential. That's what we're going to do for the first few examples here. And then we'll use that to help us do some equations here in just a little bit. Okay. All right. So let's start. Let's go logarithm to exponential first. So rewrite each logarithm as an exponential. So keys to the kingdom up there, the blue to red, logarithm to exponential. So here we have a log base 3 of x equals y. So if we're going to rewrite that as an exponential, what is the base of the exponential? The same as the base of the log. So that would be 3. What is the exponent for the exponential? Y. Whatever the log is equal to. Then there's only one place to put that x. And that's all we're doing there is just rewriting it. We're not trying to solve anything yet. We'll get to that in a little bit. Get to do plenty of that later on. Right now, we're just working on rewriting a logarithm as an exponential. Let's say we had log base 2 of x equals 3. here's a logarithm. We want to rewrite it as an exponential. So what's the base of my exponential? Exponent. What is it equal to? There you go. Now this would be a case where rewriting that logarithm as an exponential allowed us to solve for x. That's kind of the idea where we're headed. Okay, because we can work out now 2 to the third power. Over here, this looks a little weird, but this is math we can do, right? So that's the purpose of doing that. Okay. We're not even going to simplify that out. We're just rewriting. Let's say we had log base 5 1 over 25. Here we have log base 5 of 1 over 25 is equal to x. All we're doing is rewriting it as an exponential. What's the base? Exponent? X. What's it equal to? Yeah. Now that looks a lot like the equations that we did the last couple of days, right? So here we're taking a log equation, writing it into something that looks like what we've done. That's the whole thing. That's what mathematicians do. We try to turn something into something we already know how to do. Let's go this one. Log base 4 of 16 is equal to x. Rewrite that as an exponential. What's the base? Exponent equals. Yeah, and again, that looks like what we've done in the last couple of days. Very, very easy equation form, but that's what we're after right now. All right, the next couple are those what we call common logs. Common logs are log base 10 and the natural log, ln. Okay, so log base 10, when they write that, they don't usually put the 10 down there. Okay, they write it as just log x equals 3. That's how they'll write log base 10. They don't usually put the 10 down there. Sometimes you will see it there, not very often. Okay, so if there's nothing written there as the base, it's an understood 10. The reason is because we live in a base 10 number system. Everything we learn to count is based on the tens positions. So like the 1 spot is 10 to the 0 power. The 10 spot is 10 to the first power. The 100 spot is 10 squared. We live in a base 10 number system. So plain log, log, is log base 10. So when you see that, you got to imagine, hey, there's a 10 there. If it helps you to write it there, do it. I mean, it's okay. There's nothing wrong with it. It's just they don't usually do that. You're not going to see it given to you that way. So if we're going to rewrite this as an exponential, the base of that would be a 10. What would the exponent be? 3, and it's equal to x. And there's one that, hey, we could solve that right away. We don't even have to do any work other than just work out what 10 to the third is. Okay. The natural log is log base e. Remember, e is that number. It's kind of like pi, but it's 2.71 and some bunch of decimals after that. So natural log is abbreviation for log base e. So the base, when you see ln, is e. So if we're going to rewrite this as an exponential, what would it be? Yeah, very good. E to the y equals x. Okay, so not too often are you going to see them write log base e. They're going to use ln most of the time. Okay. I have seen a few textbooks that put a log base e in there just to try to screw you up, just to make it look weird. But ln is the same thing as log base e. Okay. All right, so let's go the other direction. Let's rewrite an exponential as a logarithm. So let's start with 3 to the x is equal to 27. Okay, so remember the little cheat code is that whatever the base is, that becomes the base of your logarithm. Whatever the exponent is what your logarithm is equal to. A to the x, base is a, exponent is x. What the exponential is equal to is what you're taking the log of. So, how would you write this one? It's not times, just say of. Yeah, because it's not really multiplication that's happening there. Of 27 is equal to x. Yeah, right idea. Just got to get the verbiage in the right way. I'd hate for you to go to somebody else's class and say it the wrong way, and then we're like, "Who's your teacher?" You teach you right there. And then I'd get a nasty email from somebody. Yeah, I'm sorry. All right, write that one as a logarithm. What's our log base? Yeah, log base a of equals. Very easy. Very good. Okay. Let's get to one that looks more like a college level problem. 10 to the x plus 1 is equal to y. So what's our log base here? Yeah, so how do we write that? Just log. Don't put a 10 there. Just leave it log. Of equals. Very good. Very easy thing there. One more. That definitely looks like a weird one. Similar to one of those that Easy asked about earlier in section 6.3 at the square root in the exponent. So how do we rewrite that as a logarithm? Natural log of y square root of x. Very good. So it's a base e, so that's natural log. Very easy to do. Okay. All right. The next thing that we're going to do, you need your calculator for. We're going to do it with the calculator and without the calculator. There are some that you can do without the calculator. There are some that you can do with the calculator. So we're going to do it both ways, okay? Because you guys got access. In Algebra 2, we had to do certain ones without the calculator exclusively because that would be problems like would be on the non-calculator portion. College algebra, that there's no non-calculator portion, but let's evaluate the logarithm. So I'm gonna do log base 2 of 16. We're gonna evaluate that. Okay, so I'm gonna do it without the calculator first, and then I'll show you how your calculator can do this. Okay, so log base 2 of 16. What you want to do if you're trying to do this without the calculator, and it's really actually helpful to do that. It helps you understand what a logarithm even does out of that. Is I just set it equal to my favorite variable, which for me is x. Okay. You can use n. You can use whatever letter you want to use. Just don't use e and don't use I or o. Those are the only three that I would never use because they look like O looks like a 0, E means something else, I means something else. So use anything else. Now, I'm going to take that and rewrite it as an exponential. How would I rewrite that as an exponential? Then I'm going to work it like I did yesterday. What does the 16, can I convert that 16 into a base 2? Yeah, it's 2 to the what power? 4, yeah. And then, so x is equal to 4. So that means the log base 2, not actual log, sorry. Log base 2 of 16 equals 4. That's doing it without a calculator. Now, with the calculator, there's 2 different ways to do that. One is with this thing called log base. And to get there, you're going to hit alpha window. I think that's right. Remember my buttons. Yeah, alpha window. And it pulls up that menu, log base. That's where that lives. If you got the TI-84, you do that. If you got the 83, I'm going to show you how to do that a different way. You can do it with the 84 this way too. The second way I'm going to show you is the way I learned how to do it, because when I was coming through, we had the TI-82, which didn't have log base on there. That's a probably since I've been teaching, they added this functionality. So when you hit log base there, it gives you boxes to put in the stuff you want. So log base 2, then press the right arrow key and it'll get you in the next box of 16 and hit enter, and you get 4. Okay, so that's a nice thing with the TI-84s that's on there that you can use. So alpha window, the alpha button, the window button, and then I think it's option 5 for log base. Okay, and that's going to give you log with a box and then a box. Okay, if you've got the TI, so this is TI-84 only, or 84 plus. Okay, if you got the TI-83, you can still do these. You're going to use what's called the change of base formula. Okay, so log base B of A. You can do that by doing the log of A divided by the log of B. Notice that's what is the base of these logs? 10. You got a button on your calculator that does that. On the calculator, there's a button for log base 10 right beside the 7. So you can do, for this one, you would do log 16 on top divided by log 2 on the bottom. Same answer. Okay, so that's the change of base formula. It also works. I will catch myself a lot of times doing it that way just by default, because that's the way I learned it. And so my brain just automatically goes back to doing it that way. This is the way most people do it now, because you guys have that nice thing, the alpha window, option 5. But this also works. Same answer, even if it doesn't work, if this is a decimal, this is going to be the same decimal. So change of base formula out of that. Okay, so evaluating with the calculator, without a calculator, honestly, don't care which one you do. I like being able to do it without a calculator on some problems. Some of them it just can't be done. Some of them you've got to use the calculator to do. Okay, so let's do this one. Log base 4 of 1 over 64. This would be example L. If I want to do it without the calculator, I'm going to rewrite it as 4 to the x equals 1 over 64. And I happen to know that 64 is 4 cubed. So that's actually 4 to the negative 3. So I know my answer is just going to be negative 3. If it's numbers I know, that makes it quick. With the calculator, I mean, it's the same. It's probably just as quick. So alpha window,
option 5, log base 4, and then the 1 over 64, I can put in the fraction just like I, like it's got it written. I can type it in just like it's written, and there I get the -3. Or I could do log of 1 over 64, close the parentheses, divided by log 4. I get the same -3. So alpha window, change of base formula. Not really, no difference in the values there, just working out. And then here on the paper, me doing it without the calculator. But it's got to be special numbers to be able to do it without the calculator. If you get one like this, let's say you had log base 3 of 29. That one is one that can't be, it's not easily done without the calculator. Because what do we know 29 is not? It's not 3 cubed or 3 squared or anything like that. If it was 27, yeah, it works out great. It's just 3 to the third power. But because it's 29, it doesn't work out nicely. So this is one of those where, hey, now I got to do it with the calculator. So I'm going to get a decimal approximation for that. So I'm either going to do the change of base, log 29 divided by log 3. And I'm going to go 3 decimal places there, 3.065. Or I'm going to do the alpha window version, log base 3 of 29. Same decimal, it's the same, it's the same math that's making that happen. So approximately 3.065. And it'll tell you what to round to on ones that don't work out really perfectly out of that. So whether you're doing calculator or no calculator, you can work those out. If I ask you to do one without the calculator, it's got to be special numbers. But you can check it with the calculator. I'm not taking your calculators away from you at any point in this course. Okay, so evaluating logs, pretty easy thing. Okay? It's like evaluating the exponentials. It's calculator work. All right, next thing is the title of the lesson was Intro to Logarithmic Functions. So let's talk about the logarithms as functions. So functions that are logarithmic have domains that are limited to only positives. Inside the log. The range is unrestricted. And by unrestricted, I mean negative infinity to positive infinity. That's what I mean by unrestricted. Always. It's kind of like you noticed on the exponentials in section 6.3 that the domain was always negative infinity to positive infinity. Remember, on an inverse, what swaps? The domain and the range, right? So the range was limited because of that horizontal asymptote on the exponential function. But the domain was unlimited. It was always negative infinity to positive infinity. It swaps on the logarithms because they are the inverse of that. So the domain becomes the range of the logarithm. So it's negative infinity to positive infinity for the range. The domain is going to be restricted. Okay, so when we're looking at a logarithm, so let's take, what letter are we on? N? Is that right? Yeah. We're going to state the domain. Range and vertical asymptote. So horizontal asymptote existed with exponential functions with a logarithmic function, you have a vertical asymptote. So here's our function. F of x is equal to log base 2 of x plus 6. Okay. In this case, anytime you're dealing with logarithms, it really doesn't matter about the base of the log. That doesn't change really anything about domain or range or vertical asymptote. Okay, you could have log base 2, you could have log base 26. It doesn't matter. All that does is changes how fast the curve happens. That's what the base does. Changes how fast the curve is happening. Okay, so what we're going to do to find the domain, let's start there, is we're going to take x plus 6, and how can we guarantee that it's positive only mathematically? How can we force that to be only positive numbers? What can I set that equal to, or maybe an inequality, some sort of math that says, okay, this is not going to be 0 or negative. Well, x is in my problem. I can't just set it equal to x because x doesn't have any value. X is just x. It's an unknown. How can I guarantee that that is positive? Greater than or equal to what? 1 is positive, but a half is also positive. So one wouldn't necessarily guarantee it. What guarantees me being positive? Greater than 0. That's the key. So we're going to set whatever's inside of the logarithm greater than 0. That's your key to being able to find that domain, that greater than 0 thing. That's whatever's inside of this logarithm, that's the part you're going to set greater than 0. We're just going to solve that. Minus 6. So x has got to be greater than negative 6. So my domain is either in set notation, x is greater than negative 6. What would that be in interval notation? Okay. I know there's a parentheses on the infinity. What's on the negative 6? Parentheses, because it doesn't have an equal to mark on the inequality, right? So that's why it's a parenthesis. My range, y, as long as y is an element of the real numbers. So that's all real numbers for that. So negative infinity to positive infinity. Now, my vertical asymptote. Let's glance at the graph of that. Okay, so to graph this, I'm going to hit alpha window, get my log base 2, and then inside of that parentheses, I'm going to put x plus 6. Okay. If I'm using the TI-83, I'm going to have to do parentheses, log x plus 6, close parentheses, divided by parentheses, log 2, close parentheses, close parentheses. A little bit more work, but what you're going to see is these two things being the same graph. Okay, most of us have the 84, so the top one is all we're going to have to do. I'm just showing both of those to show you that it's the same graph. So here's my log base with the alpha. Here's that change of base formula. Now, it looks like it stops right there, but it really doesn't. What happens there is the resolution on the screen, it can't draw that curve well enough. It keeps going straight down right here and flattens out. Remember yesterday or the last couple of days with the exponentials, it flattened out and got close to 0, or if there was a vertical shift, it moved up and it flattened out.
Here, the vertical asymptote is where it's flattening out at. So where's that number at right there? 1, 2, 3, 4, 5. There's -6. That's where it's flattening out at. It's going to match up with the number that's in your domain, always. It always matches up with that number that's in the domain. So my vertical asymptote is x equals -6. And there we found all three of those things for that problem. Okay. So graph can help. That's definitely a good thing. Let's do another one. So let's say we had g of x is equal to log of 3x minus 8 plus 3. What base is that logarithm? 10. Does it matter as far as finding domain and range and all that stuff? No, it's not going to change how I do that, okay? So if I'm going to find the domain, range, and vertical asymptote, I'm just going to use the 3x plus, or the 3x minus 8. This plus 3 on the outside is not going to change the domain at all. Because if we think about transformations, it's a vertical shift up 3. So it's not doing anything to the domain because domain is left and right. The only things that are happening to left and right are happening inside here. So that's the only thing that's going to affect domain. So anything outside of the logarithm doesn't affect domain. We don't have to worry about it. So we're going to take the 3x minus 8, and we're going to do what with it? Set it greater than 0. That's going to help us find our domain. It's also going to help us find the number for our vertical asymptote. Get x by itself. Easy math here. 3x is greater than 8. Divide by 3. X has got to be greater than 8/3. So my domain, all x's as long as x is greater than 8/3. What is that in interval notation? No bracket. Remember, it can't be equal to 0. So it's got to be greater than. So that's a parenthesis on that every time. Okay. If you had an equal to mark right here, then yeah, there's a bracket. That only happens, the red flag that happens on is when you have a square root in the problem. We don't have that here. We just have a logarithm. So this is kind of adding a red flag to the list of things that affect domain. With logarithms, you're taking it and it's got to be greater than 0. Can't be equal to 0. We can't take the log of a 0. We can take logs of positives only. What's our range? Yeah, so negative infinity to positive infinity. Writing that in set notation. Y is an element of the real numbers. What is our vertical asymptote? What? 8/3. X equals 8/3. It has to be an equation. If it's not an equation, it's not right. I will not accept 8/3 as a vertical asymptote. It has to be x equals 8/3 because a vertical asymptote is an equation of a line.
I do it when I'm writing it. I caught myself in that
Yeah.
multiple times. And
Yeah, it really a lot of times we do it when we write it and we just don't say it. But I'm just trying to make it clear that's a key thing, because guaranteed they're going to have that just plain 8/3 as an answer choice on the final, and then answer choice B might be x equals 8/3. There's a difference. If it asks for the equation of the vertical asymptote, you got to have an equation. You can verify that by graphing the thing. Okay, so this one, because it's base 10, I don't have to use the alpha window thing. I just hit the log button beside 7 and go 3x minus 8 in parentheses, close those parentheses, and then do the plus 3. Looking at my graph, 8/3, 2 2/3. So here's 2 2/3 would be about right there, and we see it turning down there. It stops drawing it, but it really is still there. If you zoomed into that spot, you would see that line showing up. If I zoom in right here, I'll actually do that, show you.
Scoot over there closer to it. I'm gonna zoom in right there around the 2. See, it got a little closer to that. If I zoom in again, I bet you see a little bit more of it. I didn't scoot over far enough. Zoom back out just a hair. All right, zooming. It's still thinking. But that line keeps going down, and it runs right alongside of that vertical asymptote. It's getting really close to it there. That's what's happening. So zoom. Kill line here. All right, you silly thing. Stop thinking. All right. Zoom 6. All right. So there we see that.
But it does keep going there, and it's just a lot along that vertical asymptote.
Okay. All right. So domain, setting it greater than 0, solving. That also gets you your vertical asymptote. And then range is always positive infinity to negative infinity. Never changes there for logarithms. Okay. Next thing is solving equations. Okay. So we're solving logarithmic equations here. Basic ones, really not very difficult ones. So we're going to solve and check for extraneous solutions. Now, the reason we have to select, check for these extraneous solutions, we didn't have to check for those in exponential equations because there's no restriction on the domain for exponential. In logarithms, there's a restriction on the domain. That means that there's something that x can't be. So we've got to check those things as we solve these equations. No idea what letter. P. So here we go. Log base 3 of 4x minus 7 is equal to 2. Okay, so here we have a logarithmic equation that has some x's inside of the parentheses and numbers on the outside. Okay. The key to solving these is using the thing we did first, rewriting it as an exponential. Turn it into an exponential equation so that you can get that stuff that's inside of the logarithm out of it. So if I'm going to rewrite this as an exponential, what's the base of my exponential? What's the exponent of my exponential? And then it's equal to 4x minus 7. Now, what's 3 squared?
9.
It's a number.
It's 9, yeah. So now we have the equation 9 equals 4x minus 7.
It looked like this really fancy thing up here, but because we knew how to turn it around, it turns into a 7th grade equation. Okay, so we take the college algebra part, the algebra 2 part, make it into a 7th grade math problem.
And then we just solve it for x. Get x by itself. 9 plus 7 would be 16 equals 4x. Divide by 4. And we get x equals 4. Now, we need to check that in the original problem.
What we're checking for is to make sure that the logarithm does not have 0 or a negative in it. If it has 0 or a negative, then that becomes an extraneous solution. So plug the 4 in. 4 times 4 is 16, minus 7 is 9.
That is positive, so that is good. So that is a check. It did work. And 3, but log base 3 of 9 is 2. If you do that in the calculator, it works. Let's do this one. Log base 4 of 4 to the 2x equals 10. Rewriting that as an exponential. So, what's the base? 4. What's the exponent?
10.
It's equal to the 4 to the 2x. Hey,
it just happened to already be set up with the same base on there, like what we would want in
what we did yesterday. So what's my equation that I'm solving? Yeah, 10 equals 2x. That's super easy. Divide by 2. 5 is equal to x.
Checking that in the original problem, 2 times 5 is 10, 4 to the 10th is positive
Out of that. We got like 3 examples left. We'll finish those in the morning, and then you'll have a work day the rest of the day tomorrow. Okay? Appreciate your patience today. Got 3 examples left.